Black holes. Black holes form when massive stars exhaust their nuclear fuel and collapse under their own gravity. The result is a singularity, a point of infinite density, surrounded by an event horizon, the boundary beyond which escape is impossible. There are different types. Stellar mass black holes, formed from collapsing stars. Supermassive black holes, millions to billions of times the Sun's mass, lurking at the centers of galaxies, including ours, the Milky Way. Intermediate and primordial black holes are more mysterious, but scientists believe they exist. Despite being invisible, black holes can be detected by the way they affect nearby matter. Gas and dust spiral into them, heating up and emitting X-rays. When two black holes merge, they send out ripples in space-time called gravitational waves. But they aren't cosmic vacuum cleaners. Unless you're very close, you're perfectly safe. And thanks to telescopes like the Event Horizon Telescope, we've even seen the shadow of a black hole. Black holes are not just space monsters, they're fundamental to how galaxies form and evolve. And we're only beginning to understand them. Gamma-ray burst. Gamma-ray bursts are the most powerful explosions in the universe since the Big Bang. In just a few seconds, they can release more energy than our sun will emit in its entire 10 billion-year lifetime. GRBs are brief, intense flashes of gamma radiation, the highest energy form of light. They fall into two main types. Long GRBs last more than 2 seconds and are linked to the collapse of massive stars into black holes. Short GRBs last less than 2 seconds and are likely caused by the collision of neutron stars or a neutron star with a black hole. These explosions are so powerful, they shoot jets of energy at nearly the speed of light. If one of these jets happens to point directly at Earth, we detect a sudden bright gamma-ray signal, sometimes followed by an afterglow in X-ray, optical, and radio light. Luckily, GRBs are rare and usually happen in distant galaxies, so they don't pose a danger to us. But if one ever went off nearby, it could seriously mess with Earth's atmosphere and life. We detect GRBs using space telescopes like NASA's SWIFT and Fermi, which constantly scan the sky. Studying them helps scientists understand black holes, the life cycles of stars, and even how heavy elements like gold are formed. They're brief, they're brutal, and they're a cosmic mystery we're still trying to fully understand. Supernova. A supernova is an explosive death of a star, one of the most violent events in the universe. When a star runs out of fuel, it can no longer maintain the pressure needed to counteract its own gravity. This imbalance causes a massive collapse, followed by a huge explosion. There are two main types of supernovae. Type 1 occurs when a white dwarf star, the remnant of a smaller star, pulls material from a companion star. As it accumulates mass, it eventually explodes. Type 2 happens when a massive star, at least 8 times the mass of the Sun, burns through its nuclear fuel and collapses under its own gravity, resulting in an explosion. Supernovae are so bright that they can briefly outshine entire galaxies. They release vast amounts of energy, sending shockwaves through space. These shockwaves create new elements, like iron and gold, which are spread out and recycled into new stars and planets. The remnants of a supernova often form a neutron star, or, if the explosion is powerful enough, a black hole. Supernovae are crucial for understanding the life cycle of stars, the formation of heavy elements, and even the expansion of the universe itself. In fact, the light from a supernova can travel millions of years to reach us, giving us a glimpse into the past. It's like a cosmic reminder of how stars live, die, and shape the universe. Neutron star. A neutron star is the dense remnants of a massive star that exploded in a supernova. After the explosion, the core that remains is so compact that its entire mass is packed into an object only about 20 kilometers wide. Imagine cramming the mass of the Sun into a sphere the size of a city. It's that dense. The extreme density of a neutron star means that a single cubic centimeter could weigh around 400 million tons. The intense gravity on its surface is 2 billion times stronger than Earth's. This makes neutron stars some of the most extreme objects in the universe. The outer crust of a neutron star is made up of tightly packed neutrons, and the core can have neutrons and protons stacked together in a dense state. These stars also spin incredibly fast, up to several hundred times per second. As they spin, they emit beams of electromagnetic radiation, like cosmic lighthouses, called pulsars. Pulsars are regularly observed on Earth, sending out rapid pulses of radio waves, X-rays, or gamma rays, depending on the star. These regular pulses allow scientists to measure the rotation rate and learn more about the star's mass, size, and other physical properties. Despite their small size, neutron stars have a massive impact on our understanding of matter, gravity, and the fundamental forces of the universe. They're an incredible natural laboratory for testing the limits of physics. Quasar. Quasars are incredibly bright and distant objects powered by supermassive black holes at the centers of galaxies. The name quasar comes from quasi-stellar radio source, because when they were first discovered, they looked like stars but emitted intense radio waves. What makes a quasar so powerful is the supermassive black hole at its core. As matter from the surrounding galaxy falls into the black hole, it forms a rotating disk of gas and dust. This disk gets incredibly hot and emits enormous amounts of energy, including visible light, X-rays, and radio waves. In fact, quasars can shine brighter than the rest of the galaxy combined, outshining even the stars within the host galaxy. Some quasars are so far away that their light has traveled billions of years to reach us, allowing us to observe them as they were in the early universe. This makes them useful tools for studying the conditions of the cosmos long ago. Despite their brightness, quasars are only visible in the most distant galaxies, and they're more common in the early universe when galaxies were still forming. They're rare in today's universe, as most supermassive black holes have quieted down over time. Quasars are not just cosmic beacons. They help scientists study galaxy formation, the growth of black holes, and even the expansion of the universe. Voids. In the vastness of the universe, there are enormous regions known as cosmic voids, huge empty spaces where galaxies are sparse or completely absent. These voids can span hundreds of millions of light-years across, making them some of the largest structures in the universe. Voids form in the early universe as matter clumped together under gravity to form galaxies and clusters of galaxies. The areas between these clusters, however, remain mostly empty, creating vast regions of near-complete emptiness. While voids might seem empty, they aren't completely devoid of anything. They can contain small galaxies, dark matter, and cosmic gas, but on a much smaller scale compared to the crowded clusters. In fact, voids are often surrounded by dense regions where galaxies are packed together in superclusters. Interestingly, these voids play a role in the large-scale structure of the universe. They help define the cosmic web, where galaxies are connected by vast filaments of dark matter and gas, leaving the voids as the empty spaces between them. By studying voids, scientists can learn more about the distribution of matter in the universe, the expansion of the cosmos, and even the properties of dark energy. Voids may be empty, but they are key to understanding the big picture of how the universe is structured and how it's evolving. Dark energy. Dark energy is one of the greatest mysteries of the universe. It's an invisible force that's driving the acceleration of the universe's expansion. In fact, dark energy makes up about 70% of the universe, yet we have little understanding of what it actually is. In the late 1990s, scientists discovered that galaxies weren't just moving away from each other, they were speeding up. This unexpected discovery led to the conclusion that something was pushing the universe apart more and more. This something was labeled dark energy. Unlike gravity, which pulls objects together, dark energy works in the opposite way. It repels. It's thought to be a property of space itself. As the universe expands, more space is created, and with it, more dark energy. This causes the acceleration to continue, making it a driving force in the universe's evolution. Despite its mysterious nature, dark energy plays a central role in the fate of the universe. If dark energy continues to dominate, it could cause the universe to expand forever, leading to a cold and distant end. Some theories even suggest it could eventually rip apart galaxies, stars, and atoms in a process called the Big Rip. Understanding dark energy is one of the biggest challenges in modern cosmology, and it could reveal fundamental truths about the fabric of space and time. Rogue planets. Rogue planets are intriguing and mysterious objects that wander through space without a parent star. These planets don't orbit a star like the Earth does. Instead, they roam freely through the galaxy, drifting through interstellar space. Rogue planets are thought to form in the same way as regular planets, out of a disk of gas and dust around a young star. However, for some reason, they're ejected from their star's orbit, either through gravitational interactions with other planets or a nearby star's gravity. Once they're cast out, these planets become nomads, unbound by any star. Some rogue planets are as large as Jupiter, while others are much smaller. Interestingly, rogue planets can still have atmospheres and even be warm enough to support liquid water, if they have internal heat sources like radioactive decay or tidal heating from being pulled by another large object. Even though rogue planets are elusive, astronomers think there could be billions of them in our Milky Way galaxy alone. While we can't directly observe many of them, we find them through their gravitational effects on nearby objects or through infrared observations, which detect their heat. Rogue planets challenge our traditional view of how planets should behave and could play a significant role in the future of planetary systems and space exploration.